So here is an interesting problem where we have a solution and we want to find the differential equation. The problem is quite straightforward the moment we understand the process of finding the solution. So what we have is y equals c1 plus c2 e raised to x. There are only two terms here. That should tell us that the equation is second order. And of course, it is linear, it is homogeneous, and it has constant coefficients. Let's see. So we know if the roots are distinct, so what are the inferences that we can make? So the roots have to be distinct. Why? Because there are no x squared, x cubed terms. The roots are real, in other words, not complex. Why? There are no cosine and sine terms. So what are the roots? We're going to find the roots first. So y, c1, the first term I could write it as e raised 0 times x, because e raised 0 is simply 1. The second term, I could write it as 2 times x. So the roots are 0 and 2. So m equals 0 and m equals 2 are the roots. If I move the 0 to the other side, nothing happens. So m minus 0 equals 0, and m minus 2 equals 0 are the factors. Now I'm going to multiply the two factors together. So we would have m minus 0 times m minus 2 equals 0, which would imply m squared minus 2m equals 0. Now that is the auxiliary equation. Now we're going to work backwards. So I see a 2 here, so I must have y double prime minus 2. I see a power of 1 here, so I would have y prime equals 0. And that is the dE. We're just working in reverse. A similar problem. Here we have y equals c1 cosine 3x plus c2 sine 3x. What can we infer? The roots are complex because we have cosine and sine terms. But the roots are not repeating. There are two reasons. A, the equation is of second order or order 2. B, there are no x cosine 3x, x sine 3x, or let me write it this way. There are no x squared, x cubed, etc. terms. So this has to be a second order equation. So how can we rewrite this solution? I could rewrite this solution as y equals e raised 0 times x. E raised 0 is 1, c1 cosine 3x plus c2 sine 3x. We know that that is alpha and that would be beta. So the roots are m1 equals alpha plus I beta, and m2 is alpha minus I beta. So, of course, we're writing it that way because complex roots occur in conjugate pairs. So what are the roots? The roots are 0 plus I times 3 and 0 minus I times 3. So m equals 3i and m equals minus 3i. Move the terms to the other side. We have m minus 3i equals 0, m plus 3i equals 0 are the two factors. So the auxiliary equation is m minus 3i times m plus 3i equals 0, which would give me m squared plus 3im minus 3im minus 9 times I squared equals 0. So m squared, those two terms would get cancelled, and I squared is negative 1. I get m squared plus 9 equals 0. So I see m squared, so I'm going to put a second derivative. And I don't see an m term. An m term would result in a first derivative. Since there is no m term, I'm going to write it as 0 times y prime, and 9 times y equals 0. So the dE is y double prime plus 9y equals 0. Here is another interesting case. So we have y equals c1 plus c2x plus c3 e raised 8x. So what are the deductions that we can make? First, the equation, of course, it is linear, homogeneous, with constant coefficients, with order 3. Reason being, we have 3 terms. B, there is a repeating root because there is, or because of, the x term. The roots are real because there are no sine and cosine terms. So how could we rewrite this? I could rewrite this as C1 e raised 0x plus C2 x e raised 0x. So this term has to repeat here because I have x over there. So the repeating root is 0 and plus C3 e raised 8 times x. So M1 is 0, M2 is 0, M3 is 8. Excuse me. So I could write this as m minus 0 equals 0, m minus 0 equals 0, m minus 8 equals 0 are the three factors. So the auxiliary equation is the product of the factors. So m minus 0 times m minus 0 times m minus 8 equals 0, which is m times m minus 8 equals 0, which would give me m squared times m minus 8 equals 0, which is m cubed minus 8m equals 0. So I have a third degree, and the next one that I see is a power of 1, so that would be of degree 1. So the differential equation has to be the third derivative minus 8 times the first derivative. Moving along, so here is an initial value problem. So before we do the initial value problem, we have to find the general solution first. So this is a second order equation. So the auxiliary equation is m squared plus, there is no first derivative, so we're going to move on to the constant term, 16m. Not m, it's just 16. If there is an m in the equation, then it means that there has to be a first derivative. So the roots are, it's easy to solve. M squared would equal negative 16. M would be equal to square root of negative 16. If I pull 16 out of the root, I would have a 4 plus or minus, and square root of negative 1, which is I. So the first root is 0 plus 4i. The second root is 0 minus 4i. We know that that is alpha, that is beta. So, excuse me, the general solution is y. We have complex roots, so we must have cosine and sine terms. So e raised alpha x cosine beta x with a c1 plus c2 sine beta x. Alpha is 0, so e raised 0x. c1 cosine beta is 4x, plus c2 sine 4x. So the general solution is C1 cosine 4x plus C2 sine 4x. Now we could use the initial value conditions. So y of 0 is 0, which would mean C1 cosine of 4 times 0 plus C2 sine 4 times 0, which would mean 0 equals 0, C1 plus 0, because sine 0 is 0. Y prime of 0 is negative 2. So we need to find y prime first. Y prime is negative 4 C1 sine 4x plus 4 C2 cosine 4x. Plug in the initial conditions. Negative 2 is equal to negative 4 C1 0 plus 4 C2 cosine 4 times 0. So minus 2 would equal to 0 plus 4C2 times 1, which would imply 4C2 equals negative 2. The reason being C1 is 0, and cosine of 0 is 1, and 4 times C2 times 1 is 4C2. So C2 would be negative 2 over 4, which is negative 1 over 2. So the solution satisfying the initial conditions is y equals C1 is 0 times cosine 4x. C2 is minus 1/2 sine 4x, which would simply give us y equal y equals negative 1/2 sine 4x. Here is another initial value problem. The equation is of third order. The auxiliary equation is m cubed plus 2m minus 2m squared minus 5m minus 6 equals 0. It looks like we've done this problem before. You might find it in one of the previous videos. It's right over here, and we found using the calculator the roots to be minus 3, minus 1 and 2. Last time we had a trivial solution. Hopefully it is not the same problem, in which case I'm going to change this. It is not. Let's just be on the safe side and call that 1. Well, yeah, we'll call that 1 too. So the roots are m1 equals minus 3, m2 equals minus 1, and m3 equals plus 2 from earlier. You could find it in one of the previous videos, perhaps part 2 or part 1. So it's right over here. we can use the calculator to find the roots. So the general solution is y equals c1 e raised negative 3x plus c2 e raised negative x plus c3 e raised 2x. We need y prime and y double prime. Y prime is negative 3c1 e raised negative 3x, negative c2 e raised negative x, positive c3 e raised 2x. Y double prime is 9c1 e raised minus 3x plus c2 e raised negative x plus 4c3 e raised 2x. Now we use the initial conditions. So y of 0 is 0, which would mean c1 e raised 0 plus c2 e raised 0 plus c3 e raised 0. So c1 plus c2 plus c3 would equal 0. Second, y prime of 0 is 1. So we have negative 3 c1. Let's go back and check something here. Okay. We evaluated the second derivative at 1 in the previous problem. Here we are doing it at 0. So minus 3c1 minus c2. So e raised 0 minus c2 e raised 0 plus 2c3 e raised 0, which would imply 1 equals minus 3(1) minus c2 plus 2c3. And the last equation, y double prime of 0 is 1. So we would have 9c1 e raised 0 plus c2 e raised 0 plus 4c3 e raised 0. So we end up getting 9c1 plus c2 plus 4c3 equals 1. Let's add the first two equations. c1 plus c2 plus c3 equals 0, minus 3c1 minus c2 plus 2c3 equals 1. When we add, those two will get cancelled. Negative 2c1 plus 3c3 equals 1. Let's add the last two equations, the second and the third. Negative 3c1 minus c2 plus 2c3 equals 1. 9c1 plus c2 plus 4c3 equals 1. When we add, we have 6c1 plus 6c3 equals 2. Perhaps I'll divide by 6 on both sides, have c1 plus c3 equals 2 over 6, which is 1 over 3. Now we have two equations, minus 2c1 plus 3c3 equals 1. I'm going to multiply the second equation by 2, so I have 2c1 plus 2c3 equals 2 over 3. I'm going to add them. So 5c3 would equal 1 plus 2 over c3. 5c3 would be equal to 5 over 3. This would mean c3 is 1 over 3. take C3 and plug it in one of the two equations, I would get C1 plus 1 over 3 equals 1 over 3, which would imply C1 is 0, and naturally C2 has to be negative 1 over 3. Plug it in the very first equation. That would imply 0 plus C2 plus 1 over 3 equals 0. So C2 is negative 1 over 3. So the solution satisfying the initial conditions is y1 equals 0 times e raised negative 3x plus 1 over 3 e raised negative x plus, minus 1 over 3, 1 over 3 e raised 2x. I could pull 1 over 3 out, e raised negative x with a negative plus e raised positive 2x. I don't like to start things negative, so 1 over 3 e raised 2x minus e raised negative x. And that is the solution. And lastly, we have a boundary value problem with a second order equation. So this is a second order DE. The auxiliary equation is m squared. We don't have a first derivative, so we don't have an m term. So plus 4 equals 0. This would imply m squared equals minus 4, which would imply m is equal to square root of minus 4. If I pull the 4 out, I would get plus or minus 2, square root of negative 1, so plus or minus 2i. So m1 equals 0 plus 2i, m2 is 0 minus 2i, and the roots are complex. They're conjugates of each other, so we must have sines and cosines in our solution. And alpha is 0, beta is 2. The general solution is y equal to e raised alpha x multiplied by cosine beta x plus sine beta x. I forgot the constants. I'll throw that in a bit. C1, C2. So y would be equal to e raised 0x multiplied by C1 cosine 2x plus C2 sine 2x. So the solution is C1 cosine 2x plus C2 sine 2x. Of course, we need the first derivative, so y prime is minus 2 C1 sine 2x plus 2 C2 cosine 2x. Now, use the initial conditions. Y of 0 is 0. So C1 cosine 2 times 0 plus C2 sine 2 times 0. Sine 0 is 0. Cosine 0 is 1. So C1 is equal to 0. y prime of 0 is pi over 2. That's what's given in the problem. So negative 2 c1 sine 2 times 0 plus 2 c2 cosine 2 times 0. First term is 0 because sine 0 is 0 plus 2c2 times 1 equals pi over 2. That would mean 2c2 equals pi over 2. So c2 is pi over 4. Therefore, the solution satisfying the initial conditions is y1 or y equals 0, which is c1 cosine 2x plus c2, which is pi over 4 sine 2x. So y equals pi over 4 multiplied by sine 2x. And that would be the solution satisfying the initial conditions. So keep in mind, if you have complex roots, the solution must have cosine and sine terms.